So far we've looked at a MOSFET that behaves like a switch, and we've looked at a very simplified version of MOSFET behavior. And we also saw how, as I change the gate voltage, the gate to source voltage of a MOSFET, and make it above VT or below VT, I get the MOSFET behaving like a switch that's turned on or a switch that's turned off. And I'm going to use that property by replacing a switch with a MOSFET and show you how to build an inverter with a MOSFET. So here's my abstract gate, and I'm going to show you what the internals of a gate are going to look like with a MOSFET. Okay, so here is my MOSFET. And I'm going to build a gate as follows. I connect the drain of the MOSFET to ground. The drain, I connect the source of the MOSFET to ground. Here's my drain. Here's my gate, and I connect the gate to the input. I apply a resistor RL, and I get some output, which goes to the output of my gate, and this is Vs. And for fun, let's say Vs is 5 volts. So here is my MOSFET connected to a resistor, and this behaves like an inverter. Pretty much as we said earlier, when I had a switch in place of a MOSFET, it was an inverter. If I put a physical MOSFET, the behavior doesn't change. Let me call this voltage Vin, and let me call this voltage Vout. Notice that Vout is taken with respect to ground, which is a source here, and Vin is also taken with respect to ground. So in this MOSFET, notice that Vin is the same as VGS, and similarly, Vout is the same as DS, by the way we've labeled the various nodes here. So let's make some interesting observations. So first of all, notice that when I looked at the inverter, the abstract inverter, its inputs were A and B, and those were logical values, okay, that took on value 0 or 1. And notice when I looked inside the inverter, I built a circuit containing MOSFETs and resistors, and there I show you values Vin and Vout, where Vin and Vout are voltage levels. And notice the static discipline is what caused the mapping between the voltage levels and the logic values. So here you will notice the extraordinary power of abstraction. The abstract inverter representation completely hid all the internal details such as power supply, such as ground, a resistor RL, and so on and so forth, and you just dealt with ones and zeros and a simple truth table. Okay, so when we build these digital circuits, we can ignore all of those when we design the circuit. However, there's a caution here. Okay, abstractions take us just this far. When you actually build the circuit, you actually have to worry about electrical engineering and current paths and so on. And really what is going on is when I connect a bunch of gates together, I'm going to connect all the grounds together and all their supply voltages together. So for example, if I have an inverter talking to some kind of a NAND gate, the inverter might have a ground connection and a ground connection for the NAND gate. Those two are going to be connected in a board or in a chip where I implement these. Similarly, when I have a power supply connection, those are connected together as well. Just that my abstract representation, my digital representation, doesn't show all of these electrical connections. I really take a very simplified view, and that's really an incredible power of abstraction. What I'd like to do next is for my MOSFET inverter, I would like to plot the values between the relationship between the input and the output. Okay, so here is my MOSFET inverter. This was my gate, this is my drain, this is my source. Notice that this was VGS and this was VDS. So VDS is the same as Vout, and the VGS is the same as Vin. Vin is node voltage, and with respect to ground, which is the same as VGS, given the labeling that I've chosen. And let me choose Vs equals 5 volts. So one thing I'd like to do is plot the relationship between Vs and Vin, between these two voltages. So let me draw a pair of axes, Vin versus Vout, and I can plot for different values of Vin, I can plot the corresponding values of Vout. This kind of a plot is called a voltage transfer characteristic, where I change the input voltages and I want to look at what the output voltages look like. So let me mark up on the Vin versus Vout transfer plot some of the interesting voltages. I've taken my ground is 0 and my Vs is 5 volts. So those are two interesting points on both the Vin and Vout axes. And then remember that the MOSFET behaved like a switch for various values of VGS. Recall for VGS less than VT, I got an open circuit between the drain and source. And for VGS greater than or equal to VT, I got a short between the drain and the source. Okay, so let's keep that in mind. And so let's take VT to be 1 volt. Okay, so in terms of drawing this plot. So here is VT equals 1 volt. Let me mark that point on the x-axis. I expect interesting behavior to happen at that point. Okay, so let's go ahead and plot V in versus V out. So let's start with the point where V in is less than 1 volt. So when V in is less than 1 volt, then clearly VGS is less than VT. So VT is 1 volt, and if VGS, which is let me just write that down just to be clear. VGS and VN are the same thing here. When VGS is less than 1 volt, the MOSFET is going to be off. So when the MOSFET is off, then the entire voltage, the 5 volts, will fall across the MOSFET. Notice I have a resistive divider RL in series with an open circuit, and so therefore all the 5 volts will fall across the open circuit, so this will be 5 volts. So when V in is less than 1 volt, the output is 5 volts. Now what happens when V in becomes greater than 1 volt? So when V in is greater than 1 volt, VGS is greater than VT, and the MOSFET behaves like a short circuit. The MOSFET behaves like a short circuit, V0 falls to 0, and then the output goes down to 0. So here VGS is less than VT, and here VGS is greater than or equal to VT. Okay, so notice that when I cross the threshold voltage, when V is greater than VT, my MOSFET switches. So this is where it switches, and my gate switches from a 1 to a logical 0 value. So what I've shown you here, the V in versus V out characteristic, is called a transfer characteristic, okay, or a voltage transfer characteristic of this little inverter device. So what we've seen is something very important. We've devised an inverter using a MOSFET, and we looked at the voltage transfer characteristic of the MOSFET. And the next obvious question we can ask ourselves is, let's use this voltage transfer characteristic and let's try to design an inverter out of it. Okay, let's try to design an inverter and see what we can do in terms of making it satisfy some static discipline. Okay, what kind of discipline will it satisfy? So here's this inverter that I've just drawn for you, and I just drew the transfer characteristic for that inverter. So let's try to understand the following. So here's a question that we might ask ourselves. So supposing I have a laptop, okay, let's call that the T1000 model laptop, and let's call this company, let's call that for kicks, Wintel, for instance. Okay, so what Wintel wants to do, Wintel Corporation wants to build a laptop, the T1000, and it wants all the gates inside the laptop to satisfy a given static discipline. If all the gates in the laptop satisfy a given static discipline, then they can all talk to each other with the same language. Suppose, for instance, that this company has decided on a standard or a static discipline with the following voltage thresholds, okay, where VUL is 0.5 volts and so on and so forth. One of the common questions we will ask ourselves in 6002X is, for the MOSFET inverter that we are given, does it satisfy these voltage thresholds? And one thing that I find quite useful is to draw it out like this. Okay, I like to draw out showing a sender and showing a receiver, and knowing that the sender needs to produce the VOL, VOH voltages, and the receiver needs to be interpreting the VIH, VIL thresholds. Okay, so for instance, I may have an inverter here, and the outputs of the inverter must satisfy the VOH, VOL thresholds. And the input here, as an example, might be some kind of a NAND gate, and the NAND gate must interpret the inputs according to the VIH and VIL thresholds. So in this particular situation, my VOH is 4.5 volts. My VOL is 0.5 volts, and then I have 4.1 volt, 4.1 volts for VIH and 0.9 volts for VIL. So let's take a look at what this system will do for the inverter that we built and see if it really satisfies the static discipline.